Very good afternoon, class. We come back to the class. We got the class on yesterday. Normally Tuesday is the tutorial and Wednesday is our 2-hour class. And today we have the 4 to 5 lecture 1 hour and another 5 to 6 depends on the group got the tutorial. So for this 1 hour, I think I will continue to give the to finish the topic 1, which in the CO1 of our syllabus, try to let the student understand what is a hydrologic cycle. So you can see, like in the previous a few lessons, maybe a few lectures, what sir is trying to let the student to relate the hydrology with your daily life. Because the knowledge is that you give the life to the knowledge until you are able to link the knowledge of hydrology in your daily life. So the most instantly you have the experience with hydrology is surely you see the rain before, and every time actually you are taking the shower in your bathroom, it's repeated the hydrology. It is repeated the hydrology process. So yesterday, we talked about the water balance, start to learn some of the equations. The most important process is we have the Department of Irrigation Drainage DID to do the measurements of the rainfall, and we have the departments, the same department doing the measurement of the surface stream river runoff. Oh, I got the message for Kwan Sing QR code. Let's put the QR code first. Yeah, please sign in your attendance while the QR code. You can see like the balance of the water, we call it water balance. And we have the rainfall fall down from the sky and will become the runoff. The runoff, which is we are measured in the river stream, and it has the losses of the evaporations. But yesterday we just talked about the evaporations. That's another two important process. One is what I call infiltrations, become the soil water. And today we will talk about more in depth in the losses. In the more specific terms, we call it abstractions. Let me share the PPT first. If you're able to see the presentation slide, the PPT, give me a smiling face, please. Hope everyone's still awake and enjoy the class in the evening. Now we are about 4 o'clock to 5 o'clock. And so you can see this, you can see now we are still in the hydrological cycle, and today we will focus on this few things, abstractions. Abstraction is mean like the deductions of the water due to several hydrological phenomena, including the evaporations. Or sometimes we will combine all these different kinds of evaporations, including the evaporations from the surface, including evaporations from the oceans or from the lake, including the transpirations from the tree. We call it evapotranspirations. All together we call it evaporations, or maybe sometimes we call it evapotranspirations. That's one of the losses. The second losses is the initial losses. When the rain come down, sometimes it's not directly go to the ground. It will stick to the tree, the leaf, the branch. When it hit the building, it will part of the water will stick at the building, the light pole, or all the artificial or the natural things. This kind of losses we call it initial losses before it's reached to the ground. When it's reached to the ground, particularly in forest, it will have the infiltration. Infiltration is where the water will infiltrate underground, become the groundwater. So these three important losses today we will talk about. And more than 100 years, a lot of researchers, scientists, civil engineers, hydrology engineers, they try to propose the model how to predict the evaporation, predict the initial loss, predict the infiltrations, and we have the measurement method. And today, I think what we are sharing is we focus on talk about these three things. A part of the water budget, we talk about the rainfall. We are able to use the rain gauge to do the measurements, which is we can get the data from Department of Irrigations and Drainage, DID, and we can get the data of the surface runoff through measurement the stream flow, which is a variable in DID as well. Now today we need to talk about a part of, let's say like the total rainfall is 100% and 50% will become the runoff, surface runoff. Where does another 50% go? It will go while the evaporations, initial losses, and infiltrations. This is the entire balance of the water. This credit go to DID, which is one of the figures is presented in managing the water resources in Malaysia. You can see in Selangor, the rainfall per year is about 2190. You see the other state as well. It will be Terengganu will be the highest, 3310, and the others is close to 3000. Is close to 3000, and some of them is close to 2000. We take the example of Selangor. You can see the rainfall of Selangor is 2190 mm. After you learn the lecture before, you know the rain gauge, and we have the rain stations. This data is accumulated from all different rain gauge and from the rain stations. Then we know that's the total rainfall per year. And the runoff in Selangor, they measure the stream, the flow in the river stream. They get the number as 760. You can make the simple calculations of 760 divided by 2190. So the runoff is coefficient is about 35%. But in other stages, in other state, maybe in Selangor, the runoff is 1690 and the total rainfall is 3310. If you do the simple calculations, 1690 divided by 3310. The runoff is coefficient is about 61%, 51%. So 51% of the total rainfall will turn to be surface runoff. This may give the opportunity for the hydrology engineer to design a better drainage system to drain off to prevent the flood. You can see a part of, like Selangor, a part of become the surface runoff, it will get evaporate through the evaporations. You can see the actual evaporations is 1280. In the previous lecture, it showed you the DID have this measurement result as well. They use the evaporation pen to do the measurements to see what's the evaporation rate. The major losses is through the evaporations. That's why before this, like Sir always simplify that for the simple calculations of the rainfall is the rainfall after divided by the runoff, we got the coefficient of runoff, and the remaining maybe is due to evaporation. Actually, it's still got a portion of the water is being infiltrated underground, but you can see the proportion is not that big compared to the runoff and compared to evaporations. Like in Selangor, only got 150. When it's fall on the ground, it will make the soil moisture and will go down to the ground, become the soil water. We see other stages is very interesting. You see Perak is total rainfall is 2420. After you see all this rainfall in various stages, Perlis, Kedah, Pulau Pinang, Perak, Selangor, Negeri Sembilan, Melaka, Johor, Pahang, Terengganu, and Kelantan. And you can see that it's in the range is close to 1,800 to about 3,300. When the rainfall time the area, then we'll get the total amount of water. This is BCM is billion cubic meter. Today we will talk about more on the abstractions, where the water go and how the water is losses. So in engineering, runoff is due to the storm event is often the major subject of study, or abstraction from the precipitation risk, those due to the evaporation, transpirations, infiltration, surface detentions, and storage are considered as losses in the productions of runoff. So evaporation is the process in which a liquid changes to the gaseous state at the surface below the boiling point through the transfer of heat energy. I think evaporation, all of you learned before in your secondary school, and when you put the water in the air conditions, the molecule at the surface of the water will escape to the air. So the water will be less and lesser. This is the process of evaporations. Temperature is the most important thing. Once the temperature is higher than the Weber temperature, and therefore the water molecule able to escape to the air, the water will be less and lesser in your bowl. Another thing is if there's a windy, this will faster the process. The rate of evaporation depends on the vapor pressure at the water surface, in the air above it, air and water temperature, wind speed, atmospheric pressure, quality of water, and size of the water body. And the very simple equations, vapor pressure, the rate of evaporation is proportional difference between the saturation vapor pressure at the water temperature and the actual vapor pressure in the air. So we can see the rate of evaporation is with the EW and EA in mm in mercury. So the pressure, different pressure at different temperature. And we have the coefficient C, which is a constant. This is the Dalton law of the evaporations proposed by John Dalton 1802. So it's about 200 years ago. The temperature is another important factor for the evaporations. If the temperature is higher, it really makes sense. You put a bowl of the water in your room. If the temperature is higher, that means it has a higher evaporation. The rate of evaporation increases with an increase in the water temperature. Regarding the air temperature, although there is a general increase in the evaporation rate with the increase of temperature, a high correlation between the evaporation rate and the air temperature does not exist. It depends on the water temperature. And the wind, if they got the wind blowing, is helping the molecule at the surface to escape to the air. The wind aids in removing the evaporated water vapor from the zone of evaporations and constantly grade the greater scope for evaporation. The critical speed, wind speed value is a function of the size of the water surface. Later you will find that Sir will let you see a few evaporation model which is able to use for the calculations. Normally in the meteorological departments or in Malaysia in Department of Irrigations and Drainage, they have their own measurement method like evaporation pan to do the measurements. In some of the conditions, if we didn't have the measurement data, we still able to use the model to do the estimations. Atmospheric pressure, a decrease in the parametric pressure as in the high altitude increase the evaporation. If you are in a hill on the hill with the high altitude, evaporation will be higher. Soluble salt, when a solid is dissolved in water, the vapor pressure, because if the water got the salt, it will influence the vapor pressure as well. Heat storage water body. A deep lake may store radiation energy received in summer and release it in winter, causing less evaporation in summer and more evaporation in winter compared to shallow lake exposed to a similar situation. Evaporimeter is the evaporation pan we use in the station to get the evaporation data. So associated with planning and operation of the reservoir and irrigation system. Maybe in the reservoir, we will put the evaporation pan there as well to do the measurements of the evaporation rate, because we want to know the loss of the reservoir due to evaporations. The amount of the water evaporate from the water surface is estimated by the following method. You can use the measurement data, empirical evaporation equations, the equation which obtained through the experiment, and the analytical method. So you can see they got various type of the water containing pan. We have a big pan and we put the water in. At different time we recorded how much the water losses. The standard pan is about 1.21 meter. You can see 1210 mm in diameter, and depth is 255 meter depth. Used by the US Weather Bureau is known as a Class A land pan. The depth of the water is maintained in between 18 cm to 200 cm, in 180 mm to 200 mm. The pan is normally made of unpainted galvanized iron sheet. Monel metal is used where corrosion is a problem. The pan is placed on a wooden platform of 15 cm height above the ground to allow the free circulation of the air below the pan. Evaporation measurements are made by measuring the depth of water with a hook gauge in the steering valve. When they first proposed this method, evaporation pans, so they put the standard we need to put on at a height of 15 cm. Let the pan put on that, and then we have the requirement for the size of the pan, the depth of the pan, and we maintain the amount of the water. We have the requirement on that. So this the pan we can see. So 1210 in diameter, and you can see that we have the wooden support. We need to put 150 cm above, and there's a height of the water, and we still have some space on that. That's space on the US Class A evaporation pan. So there's a method is commonly used because the evaporation pan is cheap. So the ISI standard pan, this pan evaporator specified by IS 55937 in the year 1970 is known as modified Class A pan, consists of pan. This one just now mentioned already, with this kind of depth and made of the copper chips and 0.9 mm thickness, thin inside and pan white outside. Colorado sunken pan. This pan 920 mm square and 460 mm depth is made of the unpanned galvanized iron sheet and buried into the ground within 100 mm of the top. So that's another type of the pan. You can see that ISI standard is using this kind of pan, and we have the different standard as well. But the first one is the common standard. But sometimes they have the different agency, they want to have their own standard. So there's another kind of the pan that have a slightly difference of the timetable to do the calculations. So the pan coefficients, evaporation pans are not exact models of the large reservoir and have the following principal drawback. The small pan is actually a scale model compared to the big reservoir. The height of the rim of an evaporation pan affects the wind actions over the surface, and the pan material is different compared to the reservoir. That's why we have the pan coefficients. When we try to estimate the lake evaporations, and we got this one is from the site measurements of the pan evaporations, and we need to times 1 coefficients because it has a scale effect there. Scale effect means like the pan is small, the lake is very big, it's not exactly the same. So we need to times 1 coefficients to eliminate the scale effect, and this CP we call it pan coefficients. And for different guideline for different places, like for the evaporation stations, you can see for the arid zone, for the area which didn't have that much of water, then we need about 1 station for every 30,000 kilometer square. And if for the humid temperature climate, and we can have a better distance because the water won't go that fast, 50 kilometer square. And the cold area, we can even to put the pan with using the last pan, we can keep for every 100,000 kilometer square. You can see the equations, which this one, the Mayer formula is one of the most famous formula. You can see the entire things we try to use the empirical equations to estimate the lake evaporations. how many millimeter per day the water will lose due to evaporation. And you can see that for the rainfall, we can use the rain gauge to understand, to know what's the amount of the water we have. For the runoff, we can measure the river stream to understand how much the runoff we have. And for the evaporation, if we have a reservoir, for the evaporations, we use the evaporation pans to do the measurements and times one Pann's coefficient due to the scale effect. And we're still able to use the empirical equation. Empirical equation is the equation proposed based on the experience of the lab data. So you can see, if we want to use the empirical method to estimate the lake evaporations mm per day, we need to get information of the saturated vapor pressure, EW minus EA, actual vapor pressure. And we consider the wind effect as well. You can see FU wind speed. And we have a coefficient K. Mayer agree with this general formula. You can see he further refined the things. And the wind speed, he put the standard like using the monthly mean wind velocity at about 9 meters. He put the standard that you need to consider the wind, and the wind, you use the monthly mean wind velocity at the height of 9 meters. 9 meters is how high is that? If one story is 3.5 meters, 9 meters is about 2.5 stories. Km is the coefficient accounting the various other factors which is not being considered. With a value is about 0.36 for large deep water and 0.5 for small shallow water. So depends is what's the kind of the reservoir. If very deep water reservoir, maybe the Km is review 0.5, and if it's not a very deep water, if you use the coefficient of 0.36. So you can see UH wind velocity at the height of above the ground, C is the constant U1. This thing we have the empirical method to do the estimation. So now can get into your mind already. For the hydrological cycle, you need to understand the rainfall and the runoff. Another thing is the abstraction, which is the losses. So the first one of the losses we talk about now is the evaporations. You can use the evaporation pan to get the field data, and you can use the empirical equations to do the calculations relate to the what's the evaporation of the lake. Mayer equation is the well established equations. You can see being used for so many years. It's had plenty of the variations. It's have plenty of the variations on that. It's considered the pressure, the vapor pressure, and it's considered the wind effects. All those other effects is not being considered. They put a coefficient K on that to consider the others. So this is a table to show you the saturated vapor pressure on that. Now give a simple equations like in a reservoir. Now we try to see whether you can apply the knowledge of the estimate the evaporation of not. So for this reservoir, the area is 250 hectare. With the climate parameter during a week, so the water temperature is 20 Celsius degree, and the humidity is 40. You can see the give the information of the wind speed 1 meter above the ground. The Mayer is say like the wind speed we want to consider is about 9 meters, is it? So this one 1 meter above It means like it presumably 9 meter, also the same 16 kilometer per hour. So it gives this few informations, the area, and estimate the average daily evaporation for the lake using the Mayer formula. Okay, now we go for the solution for A first. So you can see EW from the table just now is shown. Let me go back to the table later. We got from the table just now I show the Weber pressure is 17.54 and EA we type the humidity 0.4% and we got these two numbers. And the U9 is the wind speed 9 meter above ground and 21.9. So you can see how we get 17.54. We go back to see this table. Temperature is 20, is it? The water. Then your saturated vapor pressure is 70. It's 70.554. Now you do the estimation. EL equal to 0.36. 0.36 is not the deep water, it's the common water. That's the coefficient we use. 17.54 minus 7.02 divided by the wind effect. So we put in the number 21.9. Then you do the calculation. You will know that evaporation is about 8.97 mm per day. You make a rough estimations like if this is about 9 mm, it's 9 mm per day. Or maybe we put roughly, we got 10 mm per day. In a year is 365 days. That means that the evaporations is of this reservoir is 3,650 mm per year. And our rainfall is close to about 2,000 mm per year, is it, in Malaysia? So the evaporations at the lake is quite high. But don't worry, because the 2,000 of the area, we are including a lot of space, is not only the reservoir. So just this particular reservoir, so in 1 year, the evaporation will lose about 3,650 mm per day. It's quite a lot of the evaporation is losses. You can see the question number B, what he's asking. An ISI standard evaporation pan at the site indicated pan coefficient 0.8. So you see the CP is 0.8 and the calibration against the annual water budgeting method. If the pan indicate an evaporation is 72 mm in the week, under question, estimation of the accuracy of the Mayer method relative to the pan measurements. So now he said, okay, apart to use the empirical equation, the Mayer equations. Now please use the measurements of the evaporation pans. What's the difference of the measurement data and the empirical data? And also estimate the volume of water evaporate from the lake in that week. So you can see how we do on that. We have the evaporations is 72 mm from the measurement, is it? And for 7 days, so we need to divide by 7. And we need to time the CP, the coefficients. Then we got 8.23 per day. Because this is the data per week, we divided by 7. That means we got the data for for each day. Excuse me for some water. So you can see the difference for these two things is, the difference for the Mayer formula is, you see the measurement is 8.23 and compared to 8.97 is about 0.74. It's still acceptable because this is not a very high-tech method, it's very common use method. It's about 9%. Consider the pen measurement as the basic, the volume of the water evaporate for the 7 days. So it's just times 7 times 8.23 and times the area. You want to turn this one to be the meter, then you divide it by 1000 for 7 days, times the area, then you get the meter cube. That's the amount of the water we losses from the lake, from the reservoir in 1 week for the 250 hectare of the reservoir. Initial loss. So initial loss, you can see the precipitation before reaching the surface. Before the water reaches the surface, before it can become the evaporation, some of the water will be stick at the tree, that hit the building, will stick at the building. So this what we call interception process. Or maybe like it has a small pond before the water can flow to be the surface runoff. We call it depression storage. These are the two things. Before it's reached the ground, interceptions, a part of it may caused by the vegetation and subsequent evaporate. It's maybe we keep by the leaf and keep by the branch and it will evaporate. So sometimes we will consider these losses as the evaporation as well. It's evaporation from the tree. And it's estimated the interception loss is about 10 to 20%, but it depends on your area. If in forest, maybe it will higher up to 25% of the interceptions. Because forest got plenty of tree. When the rain on the tree and the branch will capture the water through the interceptions. So you can see, if it's a heavy rain, at the beginning of the rain, because not yet get wet, the tree, so it will capture the tree will capture the water, is it? So the interceptions of the small rain is lost about 80%. But if the rain to be heavy and heavier, all the leaf and the branches get wet already, no longer able to capture. So you can see this is a typical graph of the interception loss. When the rain intensity of the rain be heavier, so the ability for interception to capture the water is become lesser. Depression storage is when the precipitation and the storm reach the ground, it fill up all the depression before it can flow the surface. Before it's become the surface runoff, it will be trapped on that. It depends on type of soil and condition of the surface and the slope of the catchment. So the value of 0.5 cm in sand and 0.4 in loam and 0.25 in clay, different kind is more or depends on the soil type. Infiltration is more people interested and doing more investigation on that. Well, after infiltration down to the soil, we cannot see, and it becomes the groundwater that attract a lot of interested of the scientists and the researcher to investigate on that. So the infiltration is a process of the flow of the water into the ground through the soil. The distribution of the soil moisture within the soil profile during the infiltration process is illustrated in figure 3.8. So you can see if the soil, different soil type will have different infiltration. If the soil didn't have that much water, it will trap more, become the soil water through the infiltration process. You can see that zone 1, zone 2, zone 3, zone 4 to get the soil to be wet. So this is, you can see, saturation, transitions, transmission, wetting zone, And it has a very interesting, we call it infiltration capacity, FP. So at the beginning, when the rainfall, the soil not yet get wet, so it able to infiltrate a lot of water. And the same things like the interception as well. At the beginning can take a lot of water, but after that it will be saturated. Infiltration will be slow and up to the certain rate. It depends on the intensity of the rainfall, characteristic of the soil, and current of the current moisture contents. So you can see for different sandy, loam, and it will have the curve like that. At the beginning of the rain, you can see at the beginning of the rain, it changed with times. The soil not yet get wet, so that can have a lot of soil water. It able to absorb a lot. Infiltration rate is very high, able to absorb a lot of water. When it getting longer times, all the soil get wet already, it's only able to take less water. And for the various type of the soil, it will have different ability, but the curve will be very high at the beginning. After that, become constant. The pattern and trend will be the same. For this one, we have the measurement for infiltration as well. We have the simple infiltrometer, and this is the metal cylinder, 30 cm in diameter, 80 cm long, and open both ends. Cylinder is drive into ground in depth of 50 cm. I can show you the picture. This is the picture of the floodings, so infiltrate. And there is another method we call double ring infiltrometer. And this double ring infiltrometer, the outer ring provides the water jacket to the infiltrating water from the inner ring and hence prevent the spreading out of the infiltration water of the inner rings. And the water depth of the inner and outer ring are kept seen during the observation period. Measurement of the water volume is done in the inner ring only. The experiment is carried out until the constant infiltration rate is obtained. It has some of the advantage and disadvantage. Let me show you a YouTube. Maybe later. And this is the online YouTube. It's not made by me. So if anything you don't understand, I can try to help because the credit is go to the YouTube video provider. So for this one, the modeling the infiltration capacity. For the infiltration graph, you have to remember that got two things is very interesting. This one is the cumulative infiltration capacity, big FP per T, is the integrations of the infiltration capacity with times. So we integrate all the times. If 2 hours, we integrate all the 2 hours. We got the total accumulations, what we call cumulative infiltration capacity. If in terms we want to get the infiltration capacity at certain times, we can have this one divided by accumulative divided by dt. So you can see this graph is very important. In the time being, the ability to the soil to water infiltrate under the soil is become lesser and lesser. This is a small FP, and the accumulation is become more and more. This big FP TC. Horden do a good work. He gives the equation for you, a part of the measurement. Just now, like evaporation, we got evaporation pan, and for the infiltration, we got the double ring measurement equipment. And just now we have the Mayer equation for the evaporation. For the infiltration, if we didn't have the data, no need to worry. We're still able to estimate using the Horton equations. So using the Horton equations, the FP equal to FC. What is FC? Final steady state infiltration capacity occurring T to TC. So this one is already, after a while of the raining, is saturated already. So what's the base infiltration rate? Is this one plus initial infiltration rate with the curve. So you can see this thing is actually like, this is the FC is the base, is it? Then you have the logarithm curve. A bit of interruptions, I think, because of the raining. The internet is a bit interrupt. So now we get back already. Other analogous equation, we have other people proposed. We got the Philip equation as well. We got the Korsakoff equations. And you can see it's slightly different, but the entire concept is the same. They try to know what is the cumulative of the infiltration. So cumulative is the curve is infiltration, water is keep increasing, it is. Another one is the reducing. Initially, the soil not yet moisture, able to absorb a lot, after that becomes steady. Philip have the Philip equation, Korsakoff have the Korsakoff equation that do other considerations. Got the Krenz-M equation as well. So you can see like that's the things. That's a summarize of these 4 equations. You can see these examples like the infiltrations. We got the data change with times. So 5 minutes, 10 minutes, 15 minutes, until 130 minutes. 130 minutes, 1 hour and 10 minutes. The cumulative infiltration depth is like that. So if we can use this one for the calculations. This is 2 data we have times cumulative. Then we have this one. We have the incrementals. Incremental means like 10 minutes minus by 5 minutes. For the cumulative, we got 1.25. So this one minus this one, we got 0.95. So for this one, we able to get from cm, we change to hour. We got 21 cm per hour infiltration rate. After we consider the times and we try to get the logarithm and FP minus the FC, because all this data. And this is the times in hours. So you can see we're able to plot the graph, is it? So the graph is always small f. Small f is always like initially the soil not yet get wet, is able to absorb a lot of water. And after that, after the soil get wet, it's supposed like the curve supposed like constantly didn't change. This one I think using the Excel maybe didn't draw that good. And the cumulative infiltration is keep increasing the big F. So it keep increasing. And if you want to plot to see this one, small f versus big F, small fp versus big fp, this is the curve we can see. And as a Horton equation, if we use the law, we are able to change this one to be a straight line. This one is the secondary school study. You should have learned this before, how to do the simple mathematics. This should not be a problem. From a curve, Logarithmic curve change to be a line. This is the Hawthorne equations. So you can see the value of the infiltration capacity as the various time obtained for an infiltration test are given below. Determine a parameter. Now they try to use another Green-Am's equation, Phillips equation, Kostiakov equations. They give the times, they give a cumulative infiltration depth. You just do the same calculations based on their requirements. T in times T power to minus 0.5 and turn to all these things. Green-Am's, that's the equations. This one, infiltration capacity is not changed with time, changed with 1 per Fp. This is Green-Am equation. This is the favorite equations. Fp changed to T minus 0.5. And this one, ln Fp changed to ln times. This is Kostiakov equations. So there's from different equations, because different country, different researcher, they start to do the same things, and they have their own empirical data, so they propose different method. So this is some of the value like classification of the infiltration of the capacity. It's sometimes like we don't want to use the calculation, we can use this one, a simple one. If we know that there's a sand or that condition is low infiltration class, and then we can know like this is 2.5 to 25 mm per hour. This is the infiltration indices, and we have the graph as well. This indices is at the beginning, the infiltration water, the rainwater will retain, become the losses. So you can see at the different time is able to do the calculations on that, and we can use the Hawthorne cumulative infiltration volume to get the thing done. Use this for the calculations, and for typical value parameters of the Hawthorne models, and there's examples when there's the excess rainfall with the Hawthorne equations. So you just use the Excel, you can get all these thing is being calculated. That's the infiltration process using the Hawthorne equations. I think now we get through all the hydrological cycle. I think I'm not yet show you one thing is the video for the infiltrations measurements things. Now it's about 5 o'clock, and then we need to do it next time. Any questions? Any short questions? Normally the student will be very shy, and I hope you understand and learn the entire process, like a few things. I got the feedback from Shiji, no for now. Yeah, I think we have to end the class now. I hope you enjoy the class, and stay safe and stay healthy during the MCO times. So we'll stop the recording.